This is Illustrative Math, Algebra 1, Unit 5, Lesson 2, Patterns of Growth. And so 2.1 is saying which one doesn't belong. We have a tables of values, and you're looking at these 4 tables and looking to see which one doesn't belong. If we look at this first table and compare it to the other 3 tables, you can see that the x value doesn't start at 0, but these do. So table A, it's the only table where the x value doesn't start with the x value of 0. And it's also the only table that does not show the y-intercept, because the y-intercept for this one would be here, this one here, and then this last table, 0, 4, would be the y-intercept there. So looking at table B, looking at all of our other values, these are all 1, 2, 3, 4, and then 8, 0, 2, 4, 6, 8, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So this one only has, it has 0, 0, and then it has 2, 4, 6, 8. So it's the only table that shows these even x values. Table C, looking at this one, with 1, 4, 16, 64, and 256. Look at these, 8, 16, 24. So this one is growing plus 8, and so on. This one, to go from 0 to 16, you would add 16. To go from 16 to 32, you would add 16. And you can keep doing that for each of these. You can also keep going with plus 8 for these. Let's look at the last one. From 4 to 8, you're adding 4. From 8 to 12, you're adding 4. 12 to 16, and 16 to 20. But what about this one? How are you going to go from 1 to 4? Well, you can add 3, but if I add 3 to 4, that's not going to give me 16. So this one is changing by a common factor. If you multiply 1 times a number to get 4, that number, it must be times 4. If you do that to this one, times 4, yes, that does give you 16. What about 16 times 4? That is 64. And then 64 times 4 will give you that 256. So, this one is the only table that's not growing linearly. So these have a linear pattern because they're growing by a common sum. We're adding the same number each time. This one, it's by a common factor. We're multiplying by the same number each time. So this one is growing exponentially, and these are growing linearly. Okay, look at the last table. Let's see if we can find a reason for this one. It's the only one that's growing by adding 4 each time. And let's look. This one only goes to 20. These go much larger. 64, 64. It's the only one that doesn't have 64 in the values, the y values. So there's always something that you could try to find that doesn't belong with one of these tables. And it's really neat to be able to find all of the reasons. Let's look at 2.2. Okay, a food company currently has 5 convenience stores. It is considering 2 plans for expanding its chain of stores. Plan A, open 20 new stores each year. So they want you to use technology to complete a table for the number of stores for the next 10 years as shown. So we're opening 20 new stores each year. So that should be simply just adding 20 stores. See, from 5 to 25, they added 20 stores. So the difference from the previous years would be 20. So 25, add 20 to that, you're going to get 45. The difference is 20. The next one would be 65. The difference from that is 20. And continue on until you get to your, for the next 10 years. Okay, so real quick, you can see the difference each year is already showing it's the same each year. It's 20 stores. If there are N stores 1 year, how many stores will there be a year later? So let's say our N is 25. Well, the next year, a year later, for 2 years, it would be 45. So all we did was take that number and add 20. Well, if they tell us that the number is N, then we could say N plus 20. That would give us how many stores there would be a year later. Okay, so now what about the difference every 3 years? Every year was 20, but now if we go every 3 years, 1, 2, 3, if we add those together, you would get 60. So the difference every 3 years would be 60. The next part says, if there are N stores 1 year, how many stores will there be 3 years later? Well, so use your example from this one, what we just talked about, and see if you can come up with this one. Okay, the difference year to year was 20, so then we did N plus 20. The difference every 3 years was 60. So see if you can figure that part out. Let's look at Plan B. They want you to double the number of stores each year. So we're going to use technology to complete the table. So you could use your calculator if you needed to do this. So number of stores, if we start out with 5 stores, we have to double that. So doubling 5 would give us 10. Doubling 10 would give us 20. Doubling 20 would give us 40. So do you see the pattern there? We're doubling the stores each year. Well, the difference from the previous year, from 5 stores to 10, is 5. From 10 stores to 20 is 10. From 20 stores to 40, that's 20. So your difference, you can see, is changing. But what about your factor? What times 5 gives me 10? It would be 2. What times 10 gives me 20? It would be 2. And what times 20 gives me 40? That would also be 2. So you can see now that your factor is staying the same. So you would go on to complete this table. So what do you notice about the difference from year to year? We just talked about that. It's changing. But what about the factor? The factor is the same. It was 2 every time. If there are N stores 1 year, how many stores will there be a year later? Well, this time we're not adding, we're multiplying. So if we have N stores, we took your number of stores and we multiplied it by 2 to get the next, and then times 2 to get the next. So you would take your value and it would be 2N. Now it says, what do you notice about the difference every 3 years? Well, we have 5 and then 10 and then 20. Every 3 years, it's going to continue to change. But what about your factor every 3 years? Let's look. If we're looking at this table, 2 times 2 is 4, times 2 gives us 8. So the factor every 3 years is going to be 8. So our factor every 3 years would be 8. If there are n stores 1 year, how many stores will there be 3 years later? So we just did our 1 was 2n. You took your factor and multiplied it by the number of stores. But now they're asking for every 3 years. So see if you can come up with that one. All right, looking at 2.3, flow and followers. Here are verbal descriptions of 2 situations followed by tables and expressions that could help to answer one of the questions in the situations. You have situation 1 and situation 2. Situation 1, a person has 80 followers on social media. The number of followers triples each year. How many followers will she have after 4 years? So she starts with 80 and she's tripling. That's not adding 3. That would be multiplying by 3. So if you had 2 followers and you multiplied by 3, tripled that, you would have 6. Then multiply that by 3, you would have 18. Okay, so they started with 80 and then they're tripling it every year for 4 years. They want to know how many she's going to have after 4 years. So we need to find the expressions that would go with that. Well, this one right here, if I have 80 and I want to triple that, I'm going to multiply it by 3. Then if I want to triple that amount, I'm going to multiply it by 3. And this is going on 4 times. So this would give us the expression for situation 1. So we know A would match. They start at 80 and triple every year. Let's look at this table. This table starts at 80 and it goes to 83. Well, that's adding 3. Adding 3. Adding 3. This one is, okay, so we were adding 3 to every one over here. This one, if I do 80 times 3, you get 240. And then 240 times 3, 720. And 720 times 3, and then this times 3. So this one is multiplying by 3. Okay, so let's look at situation 2 real quick. A tank contains 80 gallons of water and is getting filled at a rate of 3 gallons per minute. How many gallons of water will be in the tank after 4 minutes? So they are adding 3 gallons of water per minute. Okay, so they're adding it. This one was tripling it because it was multiplying by 3 every time. So looking at these, we can see that this table is multiplying by 3. This table is adding 3. So this is table E, and it needs to go with situation 2. This is table B, and it needs to go with situation 1. Okay, so we've covered B and A and E. We've looked at those. Let's look at the expression for situation 2. It starts with 80 and then it's adding 3 every time. So looking at these, it looks like C would be the expression. It starts with 80, it's adding 3 every time. 83, 86, 89, 92. It matches the table. So situation C would go with situation 2. And then we've got 2 more. We've got D and F. So looking at these, we've got to figure out which one goes with that. So I want you to see if you can figure out where the expression D goes and where the expression F goes. See if you can figure those out. Okay, let's look at the lesson summary. So a student runs errands for a neighbor every week. The table shows the pay he may receive in dollars in any given week. So he runs an errand and he gets $10, then $15, then $20, then $25. You can see the common difference. They have a common difference or common sum. They're adding 5 every time. Here's another situation. This one, a student at high school heard a rumor that a celebrity will be speaking at graduation. The table shows how the rumor is spreading over time in days. So it goes from 1 to 5 to 25 to 125 to 625. The factor from previous number, it's multiplying by 5 every time. Okay, once we recognize how these patterns change, we can describe them mathematically. This allows us to understand their behavior, extend the patterns, and make predictions. In upcoming lessons, we will continue to describe and represent these patterns and use them to solve problems. So looking at these, if this one was adding 5 every time, so it's plus 5, and so on, this one would be a linear growth. This one is multiplying by 5 every time. It has that common factor. This one would be growing exponentially. It's an exponential growth.